what I am going to talk to you tonight about is 21st century Texas, climate, water, science, and society. And the main takeaway I'll leave you with tonight is that Texas's climate has changed in the past, it's changing currently, and it's going to change by the end of this current century in ways that we haven't seen before. These will be unprecedented changes in terms of climate, and it's going to have significant impact on many aspects of Texas and its society. So with that, what I want to start with is a brief outline of what I'll be talking about. I'll go through what climate science predicts will happen in the future based on principles of physics. Then we'll talk about this 100th meridian climate boundary. I'll define that, and that runs through Texas. Then we'll talk about past and future climate change and how we can reconstruct it. And then we'll focus on Texas. And once we go through reconstructing the changes and projecting the changes going forward, we'll talk about impacts on Texas's water, economy, and society, and end with pathways to solutions and maybe a question I'll leave for you all to address or to ask. Are there reasons to be optimistic? So as I said, we'll start out with what does climate science predict will be consequences of a warmer atmosphere. And this comes from the Intergovernmental Panel on Climate Change and the 4th U.S. National Climate Assessment. These are pretty extensive studies published about every 5 years. And the IPCC, the first one, that's international in scope. And the second one is just looking at impacts on the U.S. And the 2018, the 4th National Climate Assessment, I was one of 300 co-authors. And the Intergovernmental Panel on Climate Change usually has on the order of 1,000 people, scientists, engineers, policymakers working on it. So I often find these as very useful compendiums, consensus documents to say, what is the vast preponderance of the scientific community, of the experts around the world? What do we know for sure? What are the things we know with certainty? What are the things of which there's uncertainty and we are more speculative about? And how do we take these uncertainties into account? But oftentimes there's so much rhetoric about climate change. I think it's really valuable to go back to these sources. So from these sources, the predictions are that as the atmosphere warms, there'll be more evaporation over the oceans because the ocean's warmer, more water will evaporate. That will put more water vapor into the atmosphere. And all of the things being equal, that will lead to more intense rain events. By the same token, as the atmosphere warms, there'll be more evaporation over land. And at some point, the soil moisture is expended that's in the landscape. And that soil moisture, when it's gone, it no longer serves in its role to mitigate against droughts being more intense than they would be otherwise, being more longer than they would be otherwise, or even occurring in the first place. So if we have a warmer atmosphere, we can expect longer and more intense droughts. And thirdly, with a warmer atmosphere, the ocean surface temperatures will be warmer, and that will lead to more intense tropical storms and hurricanes. This is just a consequence of, as we're probably familiar, right? The temperature at the surface of the ocean tells us something about how intense a storm might be, because that temperature, that heat at the surface of the ocean is kind of like the engine room that's stoking the power of the hurricane. And that's just a simple consequence that we would get from thermodynamics. And I would point out that each of these predictions here is based on a principle of physics and chemistry that there's no debate about. As I said, there's often a lot of rhetoric about climate change, but no one debates the physical and chemical principles that these predictions are based on. So given that format, we'll come back to it a little bit later. I wanted to lay that out. And for now, what I'd like you to do is to imagine what North America looks like from space. So you close your eyes and conjure up an image of North America, and maybe you're flying the space shuttle upside down and looking down at Earth, and you come over North America, and what does it look like? And I'm not talking about those images you saw showing the path of totality. That's happened in the past, but this is now something we're talking about today and in the future. What does North America look like from space? Okay, you can open your eyes now. Does it look something like this, what you see on your screens? And I presume you can see my cursor, yeah, as I'm wiggling it around in the southeast US.
Yes.
Thank you. Okay. So the southeast US is humid, it's lush, it's green, the vegetation is healthy because of those climatic conditions. And as we go across to the western US and the southwest US, not so lush. In fact, it's quite arid and not so green at all. And there seems to be a boundary about halfway across the country between the humid to the east and arid to the southwest. And that boundary, that change in sort of climate zone, occurs right around the line of 100 degrees west longitude. And that's also known as the 100th meridian. So the idea here is that this climate boundary has actually, I'll show you data this evening that shows that this boundary in the past has moved in significant ways, and that the projections are that this century it'll move in ways that are unprecedented compared to the past. So we're going to refer to this wet-dry boundary as the 100th meridian. It was a phrase coined by someone quite a while ago, and I'll show you what went into that. But for now, just keep in mind we're using it euphemistically. It's not like the line of longitude is going to move. It's going to stay there. But the 100th meridian climate boundary will move. Okay, and you can see that Texas is kind of in a climatological hotspot. And by that, I mean, it's subject to many of the changing forces of climate. Texas is squarely in the middle of a couple of these. By being part of the arid Southwest US, part of Texas is perennially drought prone. So there's that climate risk. And then it's on the Gulf Coast. So as you guys know better than me, right? We're subject to these coastal landfalls of tropical storms and hurricanes. So it's kind of like a climatological bittersweet spot, if you will. And we'll return and talk about that in a moment. But just keep in mind that you could garner this just from this satellite imagery. And so now where are we actually specifically located? Where does this boundary go through? Well, it's not going through where y'all are. That's Houston right here, right? This gray scar in the landscape. It's going through Austin, which if we follow my cursor here, I'm tracing out the Balcones Escarpment up through here. And here's the Colorado River meandering right through, and X marks the spot. So right there is where Austin, Texas is, close to, but not right at the 100th meridian. And of course, as we go further west, right now the nearest sizable town to the 100th meridian is San Angelo, West Texas, to give you some context there. Okay, so that's sort of this large scale look. And now let's zoom in on Texas a little bit. And so here's the outline of Texas, and this is the end of August 2010. And this is a way to use satellite data to basically tell us vegetation health. So again, where the image is showing us green, the vegetation is healthy. Where it's brown, vegetation is not so healthy. Where it's white, the vegetation is absent. And you can see coming down off the panhandle, the eastern panhandle of Texas, that line, that's the line of 100 degrees west longitude. That's the 100th meridian. So that's actually a pretty good call someone made over 100 years ago to denote the boundary between where it's humid and where it's actually quite arid. Okay, so this is end of August 2010. I'm now going to roll the clock forward 365 days, one full year. We'll go to the same date, end of August 2011. And if everyone could unmute themselves for just a moment, I'd appreciate it. Just go ahead and unmute yourselves. I'll give you a second to do that. Okay, excellent. And now here we go.
Whoa.
I'm really glad I unmuted. You know, usually when I give, even when I gave this talk to 500 landowners in Texas, or whenever I give it to any kind of public audience, there's an audible gasp in the room when I show this change. So let's try this again.
Unbelievable.
Yeah. Okay, well, that was marginally better. So now you guys can go ahead and mute yourselves again. And thank you for accommodating me. Yeah, so all facetiousness aside, this represents a major change, right? And that 2011 was the first year of a 3 to 4 year drought. Depends on how you measure it. That first year was most intense. It came on in the summer and lasted most intensely through the fall of 2011. We had record high temperatures. We had record intensity of the droughts. The state lost 301 million trees. And not just due to the wildfires and Bastrop, but most of them the mortality was in place. They just died not from being burned, just not having enough water. That's 10% of all the trees in the state of Texas. There are other economic impacts as well in terms of livestock loss and crop loss. And we'll come back and talk about some of the economic impacts as a consequence of this drought. So that's a recent change in Texas where this 100th meridian actually shifted for a few years to the east. And we'll be taking a look at what will happen further into the future and what's happened in the past in this regard. But for now, I'd like to take a little step back, pay a little homage to the person who coined the term the 100th meridian. It was one John Wesley Powell, shown here on the right. And John Wesley Powell, if he was a professor of geology at Illinois Wesleyan University. If you went to try to go see him during his office hours, you probably wouldn't find him in. Why? Because most of the time he was traveling by horseback all over the western U.S., occasionally on a raft down the Colorado River, led the first research expedition down the Colorado River, mapping the water resources and geology of the western United States. So he developed quite a perspective from being all over the place. And he said there's pretty much not enough water to the west of the 100th meridian. We should really think twice about this intense westward ho mentality we had to try to develop the land and bring civilization from the eastern half of the U.S. to the western half. He was saying, he made public statements that I'll show you in a minute, that there's not enough water to do this. Think of how prescient he was. He did this without, pretty sure there were no satellites to give us data or space shuttle photographs to send us images back in the late 1800s. So that was one way he was very prescient. And he made public statements, John Wesley Powell did, such as this: gentlemen, you're piling up a heritage of conflict over water rights, for there's just not enough water to supply the land. He said this to Congress. He said it in public. He said it to whoever would listen. He came up with creative ideas on how to manage scarce water resources. Unfortunately, he was not listened to as carefully as the lobbying interests for the large railroad companies. The large railroad companies were given hundreds of millions of acres of land in return for building the railroads out to the western U.S. So the railroad companies had a strong vested interest in seeing the western U.S. being developed. And at the end of the day, their influence in Congress far outshone, and they were far more heard compared to John Wesley Powell. But isn't it comforting to know, here we are 150 years later, that we no longer have to worry about the undue influence of large corporations in terms of how land is used in this country? Okay, I'm going to hold. I know you're all muted, but I'm glad, because the cacophony of laughter at my sarcastic comment would have been deafening for me, I'm sure. So Powell was really quite an individual in other ways as well. He was an officer in the Civil War, and in the Battle of Shiloh, giving the order to charge to his troops, he took on musket fire, and as a consequence, his right arm was wounded, and they had to amputate it. There he is, you can see in this image, he's without a right arm. But get this, he recuperates several months later. He says he's good to go again. He re-ups his service in the Civil War. And there he is in the siege of Vicksburg, one-armed, hunkered down in the trenches to duck musket fire. And like any good geoscientist, as he's hunkered down in the trenches, he's studying the strata on the walls of the trenches and writing reports about that. So he was quite an individual, and I think well far ahead of his time. You could just take a look at him here, and that's better facial hair than I've seen on any tech bro on 6th Street in the last 8 Friday nights in a row that I'm down there every Friday night. As if you know me, you know I'm an expert on tech bro facial hair. And I think if you really want to be fashion forward, look at someone who's as prescient as John Wesley. And I would say the thing you want to do is round up all the pants you can buy off of eBay where the waistline is 14 inches above the belly button, as shown here, because that's going to be the next big fashion forward statement. All right, well, enough with my mild obsession about John Wesley Powell. Let's move on. And speaking of the 100th meridian, we wrote a proposal to the National Science Foundation to study what the impacts may be. And the title of the proposal was the new 100th meridian, ? In other words, will this position of this boundary shown here, this wet-dry boundary, is it going to shift? And if it does, what will be the consequences? If it shifts to the east, like it did in 2011, but it shifts for a more significant period of time, look what's lying in wait for it. All of these gray areas, especially the ones in the red rectangle there, are all counties with greater than 50% population growth projected by 2050. The state itself, the demographers tell us, will double in population between 2010 and 2050. 28 million new Texans. Where will they all live? The demographers tell us they're almost all going to move into cities. So these cities will expand their footprint, their impervious cover. Those impacts of that impervious cover will be very significant. In addition, twice as many people in this red rectangular region will mean that the demand for water will go way up. And at the same time, if that 100th meridian shifts to the east and encroaches on from southwest to northeast, the Rio Grande Valley, San Antonio, San Marcos, Austin, Waco, Dallas, Fort Worth, there'll be much less water to meet the rising demand. This is not a synergy that points towards a resilient Texas. Is this a recipe for a resilient Texas? I pose the question to you, and we could come back and pose it a number of times, and perhaps we'll all collectively have an answer towards the end of this. All right, so this is the big synergistic challenge here for Texas. The rapidly urbanizing, growing population in the context of a warming planet with a regional impact of shifting this 100th meridian and this wet-dry boundary to the east. All right, so how do we reconstruct climate change through time? How do we look at climate change through time? Well, we have present-day climate, and for that, we look at what we call the instrumental record, thermometers, rain gauges. They go back to about 1900. Before then, the records aren't that reliable or they weren't kept carefully. We have to have something else. Just like if you're not going to be in town and you need to vote, you vote by proxy. So we need a proxy record or a stand-in for measuring climate back before the instruments were available. So to do that, we can do it through many ways. It's quite a number of ways. Tonight, I'm just going to tell you about two: tree rings and speleothems. All right, and then to look at future climate, we use model simulations. So I'm not going to attempt to recreate the excellent talk you heard a month or so ago from Professor Liang Yang here in my department in the Jackson School of Geosciences on how climate models work and what their uncertainties are. But let me give maybe a very short recap, perhaps for those of you who weren't able to come to that presentation. And climate models are basically these complex numerical codes run on high-performance supercomputers at universities such as UT Austin and other research labs around the world. And what they do, these models, these numerical codes, is they simulate how the atmosphere circulates, how the atmosphere interacts with the land surface, how the atmosphere interacts with the ocean surface. And you could spin these models up and have the atmosphere go forward, decades out into the future. And one really useful thing you can do with these climate models is to put in future scenarios of how we will use energy and what the consequences of that will be for emissions of carbon into our atmosphere. So, for example, if we continue using fossil fuels as we always have, or what's called business as usual type scenario, we could project out a future trajectory for carbon emissions and run the model under that high carbon emission scenario and see what the consequences are for temperature, distribution of rainfall, etc. By the same token, we could say, well, let's imagine and hope and actually do make technological advances so that renewables are rapidly taking over, a very quick shift to renewables. There's multinational accords that have binding agreements associated with them. There's federal level policy, there's corporate changes, there's personal change. Put all of those things together, policy, technology, personal choices, and say that will produce a lower carbon emissions trajectory. And then you could run the models forward there and see what differences there are in the future climate just based on the emissions of carbon scenarios we see into the future. And in that way, the models can be actually useful for saying, well, if we adopted this policy or that policy, what impact would that have 20, 30, 40, 50 years from now? So we'll come back and look at each of these in specific relationship to Texas. But for now, what I'll tell you is we'll first go to the past, how we reconstruct past climate, then we'll look at recent climate here in Texas, and then look at the future projections, and then integrate them all together. And that's where we're headed this evening. All right, so how do we reconstruct past climate? You're probably all very familiar with tree rings, right? The youngest rings are at the margin, the oldest rings are at the center. This is just a cartoon. Let me show you something real. So what we do is we go into, for example, these bald cypress trees growing on the banks of creeks, give us a really good indicator of drought. We send this core, this like 3-foot core, into the tree, and we extract a very skinny core from it, and we could count the rings and measure how thick they are, and that tells us something about past climate. Okay, I'd like everyone, if you'd indulge me, to unmute yourselves now, because I have another participatory activity coming up in the next slide. All right. Thank you, Peter Reynolds, for unmuting. Thank you, Flo Ulrich, for unmuting. I won't thank everybody, but you guys are representatives. Okay, so in the next slide, what I'm going to do is I'm going to show you a microscopic slide through one of these tree ring sequences. The oldest part of the record is down here in the lower left. Okay, the youngest part of the record is here in the upper right. I'm now going to go through the sequence from oldest to youngest, like any good geoscientist. We go from oldest to youngest, and you all tell me and shout out, tell me when to stop when I get to the wettest part of this record.
Stop. Right there.
Wow, right there. 3, wow, 4. There was 8% participation on y'all's part. And
Yes.
8% of you who participated, you got 100% of you got it right. So I'm going to assume everybody knew, but just wasn't able to chime in at times. So thank you very much. You can mute yourselves again. That tells me you all know how to, my extrapolation tells me you all know how this works, right? And it's pretty much as straightforward as that. When there's more rain, more water available to a tree, it'll grow rings faster in a given year. Each one of these rings is a given year. And when there's a drought, they grow more slowly or they don't grow at all. So that's how we can reconstruct past drought using trees. Another thing we could do to reconstruct past climate is to use formations, like mineral deposits that grow in caves. So here's a cave. Here's me right at the water table in a cave. And these things growing in the cave are called speleothems, just a fancy word for a mineral deposit growing from dripping water in a cave. How can we use this for a record of climate change? Well, that's shown in this schematic right here. This is a cross-section through a speleothem. We're to slice it, pop it open. We'd see all these lines. These are lines of equal age, showing us that the sample was maybe early in its history was this short, and now today it got bigger and bigger just by the accumulation of the calcite mineral forming from the drip water. As the water drips, it spreads out and forms an incrementally small layer of calcite over time. So something of this scale, and actually, let me see if my webcam will pick this up. I'm holding such a mineral formation. This is outside. If it grows upward, might make it to the ceiling someday. It's a stalagmite, or it was hanging tight to the ceiling. It's a stalactite. I will quiz you on which one this is, but before guessing, you take a look at the lines of equal age of the growth layers. And this is a polished surface. Here are some of these lines of equal age, these dated growth layers that I was showing you. And so in Texas, a sample this tall usually encompasses about 20,000 years of time. So much longer. If we find a tree in our studies in Texas that's 400 years old, it's like, hey, time for a happy hour. Let's celebrate. That's a really old tree for Texas. But if speleothems and trees are at a cocktail party, the speleothems are going to be looking down their noses at the callow youth of the trees, because the speleothems can be growing over tens of thousands of years. And the way they give us climate information is that the speleothems are proxies because they grow over a long period of time, and we can date their layers. They occur everywhere in the world. Every continent that has limestone has caves and therefore has speleothems. That's all continents. And they preserve these signals of wet versus dry period, much like trees do. If it rains more, that rate of dripping into the cave increases, and the rate of growth of the mineral increases. And we could measure those rates of growth. So we have two different ways that we could reconstruct past climate in Texas. Unfortunately, we don't have ice cores in Texas. It never got cold enough in Texas to preserve those. Okay. And so just a little aside, a project that we're beginning now is shown by the title here. And we're basically using these speleothems and finding the last time the last great ice age ended. That was between about 15,000 and 20,000, between 15,000 and 10,000 years ago, We came out of the last ice age. Nothing to do with humans changing that climate. That was natural warming processes. But this may be an analog for the rapid warming we're going to be experiencing this century. So we're using the past as an analog for the future. And we have caves all across the 100th meridian in Texas. So we hope to reconstruct changes in wetness, aridity, droughts over this time period of the rapid warming as we came out of the last ice age. So stay tuned for what may come out of that. And hopefully this informs us into what we may be facing this century. Okay, so that's how we look at past climate change. And now to look at recent Texas climate, well, you know how we do that. We just look at the weather. All right, so let's look at some weather patterns in Texas over the last decade or so. All right, so here is something called, what is this? This is the number of 100-degree days in Austin. Okay, so on the x-axis is the number of days that it was 100 degrees Fahrenheit or more in a given year from 2010 to 2023. I already told you about the drought of 2011, and that was record heat as well, 90 days last summer. I know you guys in Houston felt it too. I assume most of you are tuning in from Houston, but sorry if I'm misrepresenting you. So the summer of 2023 was record setting in a number of ways itself. So look at this last 14 years of record. It'll be important to say, okay, over the last 14 years, about how many days did we have? What would the average be? So that's the question I'm asking here. What's the average for this 14-year period that we're looking at? The human brain and eye is excellent at processing data. So I want you guys to unmute yourself and just shout out to me what you think the average number of days these data are showing.
50.
40.
45.
40.
Yeah.
I heard 2 50s, 2 40s, and a 45. I'm going to take the average out of those 5
50.
and another 50. Okay, so 46. It's 44. Wow. You guys are really good. Holy cow. I was right about the human brain. You didn't let me down. Your brains didn't let me down. And what do you think it was for how many 100-degree days did we have last year in Houston? I'll give you a hint. Less than the number of 100-degree days in Austin last year, 2023. Anybody know that number?
32.
45. All right. So this is something statewide that we're seeing. So I want you to keep this number in mind. Let's go with Austin here. 44. Someone please write that down. Number of 100-degree days we've had in Austin for the last 14 years has been 44. We're going to come back to that. Okay. Now we're going to go to future Texas climate. And this is where the model projections come in, what Professor Yang was talking about the last meeting of this group and what I was talking about just about 10 minutes ago. So we're going to look at model projections for what these supercomputer models show for the last 3 decades of this century. Okay, so 2070 to 2099. And that's what's shown here, the late 21st century. And this comes from this 4th National Climate Assessment document that I mentioned I was part of earlier. And I'm not a climate modeler like Professor Yang, but I make use of the data that come out of these models. So here's Texas, Oklahoma, Kansas, and the pattern here, the colors, the legend is down here, the change in number of 100-degree days. So this is the change number of 100-degree days Fahrenheit it'll be in this three-decade period at the end of this century we're looking at. Okay, what I'll tell you is that this one is the high carbon emissions scenario. So let's keep in mind that this is the change. This is not the number. This is the change. So if we go to where Austin is, right around here, corresponding here, somewhere between 80 and 90. So let's call it 80, right? How many did we have to add to that to get to the present day? Like in the last 14 years, what was that number we wrote down? How many 100-degree days were there in the last 14 years?
44.
44 plus 80. Help me out. 124. How many months is that? Help me out again.
4 months.
4 months and 4 days. Let's round it down. 4 months. Think about that. 4 months, 100 days. Does that mean every day? June, July, August, September, every day? Well, no, with weather patterns, there'll be some lows. So that means that number of days, those 4 months of days, will be spread out on the calendar. It will start likely, as if this comes to pass, if these models are correct, they'll likely start in April, like now, and they'll last till November. Like over half a year, there'll be 100-degree days. Think about that, what life will be like. I mean, I know personally, if it's more than a couple of days in a row of over 100 degrees and I'm sitting inside and trying to chill in my air conditioning in my fortress of solitude, as it were, I get pretty cranky. I get pretty miserable. I can't go outside, enjoy the benefits of being outside, which are many. I won't share with you everything I do outside, but I get a lot of enjoyment and mental health from being outside. Instead, I'll be cooped up. Well, that's my own little miserable, myopic view of things. Let's put that aside and think of how it will be for everyone and anyone, particularly people who work outside for a living and have no choice but to be outside. We'll come back to that impact on the workforce of these sorts of temperatures. But this is a very different Texas than we're looking at right now. Okay, someone seems to be drawing on the screen. I'm not sure how that works, or if we can actually control that. All right, so now let's consider the low carbon emissions scenario that I described to you through technological advances, policy changes, personal choices. Let's look at the low carbon emissions scenario results now for the same time period. That's a very different Texas, isn't it? It will still warm, right? Because we're committed to warming by all the carbon that's already in the atmosphere, right? But it will be much, much less warming, a much different kind of Texas. And so I think this shows the value of climate models. I think the results that we're looking at here are important for a couple of reasons, right? First, what this shows is that future climate is dependent on current and future human behavior. That's what this tells us. What this also tells us is something very interesting in the context of, you often hear a lot of people say, well, you know what? Yeah, I now accept that climate change is real, but it's too hard to do anything about it. We're kind of screwed. We might as well just enjoy what we have while we have it, while we're here, because it's too tough. We can't do anything about it. This shows that that kind of thinking is mistaken, because this shows something can be done about it. Will it be easy? No one said it would be. Will it be possible? These data say yes. So those are two important takeaways, I feel, coming out of this. All right. So now this is the most complicated figure we'll look at. And there's that unfortunate little squiggle there. Is it only on my screen that I'm seeing this green squiggle?
On my screen too.
Okay.
No, it's everywhere.
Okay. I don't know what caused that, but don't look at it. Whatever you do, don't look at the green thing. You try to see through it. So let's spend a little bit of time on this, because this is a fairly complicated figure. This is the drought index on the left-hand y-axis. Negative numbers means it's dry. Positive numbers means it's wet, about a long-term average of 0. And this is from the year 1000 to the year 2100. The colored things we'll talk about in a minute. Those are models. But for now, I want you to focus on the brown curve, these ups and downs. And this is the record from both the instrumental record for the 21st century and the 20th century here, and it's the proxy record going further back in time. And the proxies being used here are tree rings. So we have tree rings that take us back 1,000 years. And this is both the proxy, as I said, and the instrumental record. So you could come through here and see these ups and downs. And the downs are droughts. The deeper it goes, the more intense the drought is. The wider it is, the longer the drought is. So the ones that are wide and deep are the real big events. We can see that there were some times in the past when this whole almost 200-year period was almost entirely in drought, except for this wet period here. There's a lot of things we can glean from this. Oh, and on the right hand here is this y-axis is showing dry is down and wet is up. Okay, so that's the proxy and instrumental record. Now let's look at these model projections. So that's what the colored curves are here. And what's shown in gray on either side of the colors is the uncertainty based on those different models. So there's 17 models here in a global intercomparison project. There are at least 17 different research labs around the world that run climate models. They don't all treat every aspect of the climate system because it's so complex in exactly the same way. And it's important to understand that models are really useful, but they have significant uncertainties associated with them. So we cannot just accept at this point in time in the future, this will be how much rainfall, this will be the drought index, whatever we may be looking at, right? We have to keep in mind the inherent and large uncertainties on these models. And that's what the gray band is showing here, scattered about the colored curves, which are the different models, the gray band. So keep this in mind now. So here is the models reconstructing what the instrumental record is showing, including this drought in the 1950s. And then as the model goes forward, all the models are showing that it's getting drier and drier and drier. So that by the end of this century, the world we're looking at here, even given this significant uncertainty, is a very different world than we are currently in. And here in 2024, we're already partway towards this brave new Texas, as we might call it. How significantly different it is it than anything we've seen in the past? Well, we use the term, and one of the co-authors on the second paper here, and the first paper also used it, the word unprecedented, to characterize the drought risks in this coming century. And what do we mean by unprecedented? Seemingly like some sort of emotionally charged word that scientists aren't supposed to be tallying with. But here's what it's based on. Look at the worst case scenarios we go back through time in terms of drought. Which one of these is maybe the deepest and the longest? Maybe this one in the 1100s. Let's consider that. And we actually see that there was a civilization living in the Four Corners region of the Southwest US that gave up the ghost at the end of this 200-year period of drought. These were magical engineers of water resources that were able to live in this very dry environment. Geoarchaeologists and anthropologists generally agree that this civilization collapsed due to this extended drought. What cost will it be for a civilization to be wiped out, eradicated by a drought? Another way to sort of monetize climate change. We'll get into that in a little bit more. But anyway, we look at the worst case scenarios probably here, right? And let's compare the drought index here in about the 1150 to what we're seeing today and what we're going to be seeing in the future. That is a very unprecedented change we're going to see. That's what we mean by that term. Nothing we've seen in the last 1,000 years will come close to what we're going to be experiencing according to the model projections in Texas. Okay. You know what? I'm going to stop sharing to see if maybe, and then reshare. Let's see if dare I stop sharing? Connie's saying, please don't do that again, Jay. Please don't stop sharing. There. Okay. Gone. All right. So one more thing I want to show you on this diagram here is this thing, the 1950s drought of record. This is the drought in the instrumental record. This is the worst drought in the instrumental record. It was 6 years in the mid-1950s. Cost the state a lot of money. Cost our economy a lot of money. It cost water resources, their sustainability for a while. This is used by the state's planning agency, the Texas Water Development Board, which is charged with making sure there's water for all Texans for all purposes 50 years into the future. And the charge of the Texas Water Development Board to its water resource managers all over the state is saying, make sure you have enough water 50 years out into the future should the worst case scenario reoccur. And like, what's the worst case scenario? The 1950s drought of record. And the state continues to use that as its standard for water resource planning. And effectively, it ignores the proxy record, it ignores the model projections. And I ask the question again, is this sufficiently planning for resilience for our state into the future? Be happy to come back to that in a bit here. Are there other unprecedented climate events? There's this one unprecedented, but that's just projected. Is everything that's unprecedented things to come? Things that you're projecting, that you're using a computer to model that will come? Actually, some are already occurring if we look in the last 2 decades. And there's a whole bunch of things here that are unprecedented climate events and impacts in Texas. I don't want you to look at them all, go through them all. I'll just lump them together here by record water shortages, Hurricane Harvey and other events, record rainfall. We've had record heat, including the summer of 2023, more intense storms. These are all things that have been happening in the last 20 years and are unprecedented. Now I want to pose the question to you. How does any of this fit with predictions of the consequences of a warmer atmosphere by climate science? That was like that third slide I went through that said, here are 3 things climate science predicts will happen as a result of a warmer atmosphere. You remember those consequences? How did any of these unprecedented things fit? Well, they're all fully consistent with those predictions of climate science. Make sense? So we're already seeing the effects of a warming atmosphere. What are some of the impacts that Texas will face from these events? Let's go through a couple of them here. So one is water resources. What will be the impact? We have a 21st century mega drought on water resources. And by mega drought, we just mean a drought that's 10 years or longer. And from the model projections, you see that this whole second half of the 21st century will be the longest mega drought ever if the model projections come to pass. So the example we'll look at is Barton Springs in Austin, Texas. I assume a lot of you all have been here or know about it, but let's talk about what will happen with this aquifer based on its past record. And remember, the Edwards is a karst aquifer. That means a karst landscape or a karst aquifer is one characterized by solution features, by caves and sinkholes and big conduits. And so the Edwards is a classic limestone karst aquifer. And let's look at this data here. This is another time series like we looked at for the drought. Only now, not only are we showing the drought in red, where again, dry is down and wet is up, just like we looked at before on the right-hand y-axis. So this red curve is the drought index going up and down. And now what's in blue is spring flow, cubic feet per second, coming out at Barton Springs, right? One of the main orifices that fills up that awesome swimming pool. And that's what's shown in blue is spring flow. And we can see that every drought has associated with it a big drop in spring flow. And there's the 2011 drought as it came down to record low drought index. The flow came really, really low into almost a single digit cubic feet per second from what's sort of a long-term average of somewhere around 100. So what this shows is that the Edwards aquifer is very sensitive to climate change. It's like a hand-to-glove fit. Every drought sees a major drop in spring flow. There's a lot of reasons for concern about this, associated with water quality, water quantity, the endangered species that live in that unique habitat. They're endemic to the Barton Springs region. Lots of reasons for concern. And plus, simple thing, one of the nicest swimming holes in the world in a major urban environment would go dry. All right, so let's consider that shallow karst aquifers are very vulnerable to drought. The Edwards aquifer, as I mentioned, is karst, but it's also very shallow, just below the surface. So we have these big channels, these caves, these conduits, and in a drought-prone climate, every drought is going to be felt because there's this direct connection with the surface. If it rains a lot, the aquifer fills up. If it's a drought for a long time, the aquifer drains quickly. This is not typical of every aquifer, but it is typical of a shallow karst aquifer. If I showed you the Ogallala aquifer, it'd be a very different story. All right, so how do these impacts change when we now urbanize the region? Well, when we urbanize a region, we introduce impervious cover on the landscape, takes away a lot of the ability of the landscape to filter the water. So there's impacts on both water quantity and water quality. The water runs off quickly and it carries contaminants. There's really then what we would call a quadruple whammy that something like the Edwards aquifer faces. The quadruple whammy is, what are the four whammies? It's shallow, so whatever happens at the surface is felt in the subsurface. It's karst, so we have these big conduits, these big connectors from the surface to the subsurface. That means the response to what's happening at the surface is even quicker. If it's in an urbanizing environment, that's whammy 3, because we introduce all these contaminants and impervious cover, and it's in a drought-prone region. So that's the fourth. Those are the four whammies of the Edwards Aquifer. And that's what one example of a very important resource for Austin, San Antonio, largest city in North America, reliant essentially entirely on underground water, will be subject to in the 21st century. Okay, so does the state of Texas have a plan for addressing these climate change challenges? I'm going to leave this for a little bit. Anyone who's interested in my experience at the Texas legislature related to how the ledge could address the climate change challenges Texas faces, I'll be happy to share with you my experience, perhaps during the Q&A. But I'd like to turn now to ask, what will be the costs of these impacts on Texas climate change from drought and heat extremes? How can we best assess these costs? Well, the costs of impacts of Texas climate change from drought and extreme heat, I already talked about the 2011 drought, the livestock losses. That was about $9 billion. We know this from the news headlines because that was the big thing, as well it should be. That's a big loss. But what wasn't taken into account is, how about the losses? How can we monetize the lost ecosystem services from 300 million trees that were killed? There were a lot of important services lost that we could just add up by considering what services a tree gives us or a forest gives us. You could actually add another 30 billion to that. And all of a sudden, it's a different ballpark of costs that we're looking at. But I'd like you to consider this further. As much as $39 billion from one drought event is costing the state, let's consider this. In this century, there'll be heat extremes that are going to cause physiological and cognitive impairments that will lead to workforce productivity losses, both from absenteeism, but also the people showing up. Studies show that we're just not as good. We're not as smart. We're not as efficient at work when it's warmer. Look at the cost there, 500 billion, $500 billion by 2050, annual, $500 billion a year annually for the country. Out of all the 50 states, guess which one is most subject to these costs, to these losses? It is Texas. When you add on to that the social inequities of these impacts, right? A lot of these impacts are concentrated on marginalized people in terms of socioeconomics. Poor people bear the brunt. They have less agency, less ability, less free time, less expendable income to do something about what they're facing. And these just multiply the effects of what's above. So I've spent a little bit of time here monetizing these costs. Why? I think it's important to monetize the impacts for decision makers, because I think that's what gets their attention. If we're going to move off the mark of business as usual, especially in the state of Texas, I think we have to be looking at these bottom line costs in order to motivate people to make different decisions that are being made. And what might be an example of a decision maker? Oh, perhaps a state level resource planning and lawmaking that does not acknowledge climate change. All right, so I want to end with just a couple of slides on paths to solutions. And solutions can come from policies and practices at all scales, from global to local, technological advances, education, and personal action. I just want to delve into the 18 things one could list in detail under each of these and talk about what I consider two promising examples. One is reimagining how we build our cities, and the other is engaging communities with STEM. So first, reimagining our cities is this urban heat island effect, which I'm sure a lot of you are familiar with. Right? When we look at this blacktop and we look at the concrete and the cars and the trees, what part of this area? This is Northeast Austin, a Walmart, and we did a heat mapping exercise with my class, and we used infrared imagery to determine what's the hottest part of this landscape. You might say maybe the cars, not the trees probably, maybe the blacktop. Well, let's take a look. Look at this infrared image here, right? Coolest are the purples down at 76 degrees. Hottest is the bright yellow, 120 degrees. So the trees are good, shade's good. The cars are hot, but the most uniformly hot surface is this blacktop. And that's because of the radiative forcing that happens when incoming radiation from the sun is absorbed by the pavement and re-radiated into the atmosphere as long-wave infrared radiation. That warms the surface. That's why cities have this thing called the urban heat island effect. And above ambient, it's like a 15-degree increase above ambient in East Austin as a consequence of this. And I want you to consider the 4 months a year we talked about where it's greater than 100 degrees F. Now add 15 to that, to the urban heat island effect, and consider that you're working in construction or roofing or as a first responder. A friend of mine who's a first responder going through the Houston Fire Academy recently came out and with our friend group who work out outside on Saturday mornings, and he brought all his gear as a first responder. 70 pounds of gear on top of that. This will be a very different Texas that we're looking at. I want you to consider what you'll be doing if you're around at this time, or what your kids or grandkids will be doing in this environment, or will you even be in Texas? So I think we could reimagine our cities. And by that, I mean these impervious cover impacts. There's an urban heat island effect. I mentioned, like with the Edwards Aquifer, the impervious cover has a big impact on water quality. There's a lot of things that are negative when we pave a landscape. And so there's a great opportunity here. How many brand new buildings in Austin or Houston or wherever you live, whatever city you live in Texas that's growing rapidly, how many of them have design elements to mitigate against the urban heat island effect? Well, it's a kind of a pet peeve of mine that the answer is like 0, pretty much. So here's Central Austin. This is just, I'm not picking on this particular new development, but it's one example that's typical of everything I see in Austin, driving around town and photographing this. Here's the street. Here's the path where cars go and drop people off when this building is done. And I got in here and I was just about to touch that building, touch the curb. Touch the building, touch the curb with my wingspan. That tells me that the design of this landscape is for 0% pervious cover and 100% impervious cover. We could do so much better than this. And it's so easy to do it when we're designing all the new developments that are going to house the 20 million new Texans to come. It's hard to do retrospectively to take a city and add back in pervious cover, take out the impervious. But for new expanding developments, this is the easiest thing to get out in front of. Yet we have no legislation that's doing that. You say, maybe that's too hard to do. Well, we could look at Save Our Springs in Barton Springs. For the reasons of keeping water quality high in the springs, the citizens got together, formed this alliance, Save Our Springs. It was a citizen-led initiative in the early 1990s, and they were successful. They fought City Hall, and they won. And they restricted development to 15% impervious cover in the recharge zone of the aquifer. We did it for keeping the water quality high in a little swimming hole. Why aren't we 10 times as much fired up in arms about it for climate mitigation? We have to move off this mark. And the last example is engaging communities in STEM. I'm just going to go through those and go right to the end and tell you in the Q&A if there's questions about that. I'll be happy to share with you. Thanks for your attention. Here's a bunch of resources about various things that we are currently working on in this regard. Thanks for your attention.
Thank you, Jay. That was really, really informative and a call to action for all of us. What we can do now is if you want to ask Jay a question directly, just raise your Zoom hand and that way I can see you and call on you and we can keep that organized. And we already do have some questions in the chat. So Marvelyn can convey those momentarily, but let's just wait first and see if someone would like to shout out a question for Jay.
Shout it out. Okay, well, we'll do this like in my class. I'm going to just randomly call on people. It's called cold calling, and the students love it, and you'll love it too.
I bet.
I'm teasing. Extra credit. You ask a question.
Maybe if we start with Peter's question and it probably get the ball rolling.
I think I heard
Um,
someone just call my name, asking a question.
Yeah, this is Trey. Hi.
Hi.
So, okay. I fly planes, in planes. I have air conditioning. I drive my car everywhere, right? I'm not changing that behavior right now. Do I need to change that behavior right now? How much impact does that have versus other sources of carbon that are impacting us?
Yeah. Well, transportation, whether it's by air, by car, anything other than a bike or public transportation or walking, yeah, there's a big carbon footprint to that. But you could rightly ask, I'm just one of 8.5 billion people. What possible difference can I make? And asking it that way is correct. But yet, on the other hand, it's not a correct way to look at it, because it's only when everyone buys in, or a critical enough mass of people buy in, can those differences add up and make a big difference. It's a great analogy. You might find it in the literature. It's sort of a parable called The Tragedy of the Commons. And it's about shepherds on a meadow, and everyone just wants a little bit more, and they take a little bit more, and they use a little bit more, and they think it's at no cost to the larger group. But when you multiply it through the whole group, it actually turns out to be a big cost. So I say, I'll couch it this way too. Some people say, Jay, are you optimistic or pessimistic about the future? And the way I look at it is this. There's sort of two groups of people. One who say, you know what? It's not worth doing anything about because it's too hard to change, or it's a hoax, whatever it may be. Those people say nothing should happen. And then there's another group of people who say reasonable actions by many people, attainable actions by many people, can make a big difference, and therefore it's worth doing. It's only if a critical enough mass of people in the world adopt that second attitude that there's a chance for a good outcome in the climate crisis we face. On the other hand, if a critical mass of people adopt that first attitude, it's not worth doing anything about, it's too hard, we're screwed, then we know what the outcome is going to be. There'll be no change, there'll be no action, and it will be a bad outcome. It'll guarantee a bad outcome. So I say, as a result of that reasoning, I have no choice but to be optimistic. And I am, and I remain optimistic, because I think it's important to educate others and to share that attitude with as many people as possible. It's simply the calculus of the tragedy of the commons, that if we all adopted change, that's not going to solve it. Personal change by 8 billion people will go a big way towards it, but it's not going to be the only thing that's going to change. There has to be intergovernmental accords that are binding. There have to be technological advances. There has to be a quick and rapid transition to renewables. All of those things have to happen for a good outcome, and they're all possible. Sorry, Trey, that was probably more than you asked for.
Okay, Shyla Ray, why don't you ask Jay a question?
Hi, yes. So I had a question focused more on, I guess, adaptation and resiliency. And yes, the whole idea of lowering our carbon emissions, should be happening. However, this has been an ongoing issue for so long now, and we're already seeing so many weather changes and catastrophic events because of climate change. So how do you think we can focus more on adaptation and focusing on resiliency also?
Yeah, thanks, Shyler. A great question. I think, again, just like I said, all these solutions, there's no one silver bullet. I also think you could break them all down into adaptation, as you're talking about, adaptation/resiliency, and mitigation, right? Mitigation is taking action now, so you'll arrest the forces that are driving, like keeping carbon out of the atmosphere. That would be mitigating against future change. Whereas adaptation, resilience, is building seawalls, let the carbon, don't do anything about mitigation, let the carbon rise, but as long as you're building a more resilient infrastructure in society, you'll be ready for it. I think personally, there's no question that we have to be doing both. Because adaptation will be made easier and be more successful if and only if we undergo mitigation.
Marvelyn, why don't you let us hear from the chat stream? What are you seeing there?
Well, Peter had an interesting question that kind of tied into a couple of others that came to my mind. And his is, what would a 25 or 50-year view show? And this is referring back to your two US maps or Texas maps of the difference between the drought year and the non-drought year. And what would a view of a bad drought in the 50s look like? Which I think goes on to ask, would, if you compared that, say, a 1950s comparison between those two shots and the 2011 comparison between those two, would the impact be similar? Or are we seeing increasingly bad impact? Or how are maybe longer recuperation times between droughts? How are you seeing those comparisons between, say, 5 decades ago versus now?
Okay. All right. Thanks. A lot of questions in there. I'm going to try to,
Thank you.
I'm going to try to unpack them. And maybe
right.
I'll just go to Peter's question right there in the chat.
Sure.
Yeah. So how would that view, that 2011, the thing that you guys had audible gasps about, look like in the 50s? The 50s was 6 years. 2011 was just like 3 years. So it was shorter, but 2011 was more intense. So similar view in the 50s probably would not have looked as white or as ungreen, but it would still have been maybe 3/4 of the way towards what that looked like. And it would have lasted 6 years, which is what the 50s drought was, as opposed to the 2011 drought. Now, what would a 25-year or 50 view show? Well, just think of what we're looking at as something more intense, right? So remember that long-term thing that showed the projected drought index going down, down, down all the way to 2100. It was way more intense than our historically most intense drought of 2011. So that means it's going to be much drier on that same landscape. And if it lasts for 25 or 50 years, well, then that's a really hard-baked drought. And so it will look much drier, much more intense, much more barren than the images that we've looked at. Unless mitigation comes to pass, adaptation, can we build enough reservoirs to cover the all the needs that we have? I think some of the technology we have to be looking at, I think we have to get beyond reservoirs, as my colleague Todd Hallahan at University of Oklahoma likes to say, and has shown. A reservoir is like the best way to evaporate and lose as much water as possible, right? It's this wide, shallow body of water baking under the sun. And so that is not the best way to preserve a water resource. San Antonio, which is challenged to provide enough water for its citizens in the future, and Austin is starting to look at this, and many towns in Texas are, something called aquifer storage and recovery, whereby during wet periods, you route all of those floodwaters, you route them into recharge features into the aquifer, and you channel them so that the water goes down into the aquifer instead of running off into the Gulf of Mexico. And then you're banking that water for when there were drier times. You're raising the level of the aquifer, you're storing it until you need it during drier times. So we need to start ramping that sort of technology up, as well as personal conservation, as well as talking to people in the state legislature about what it is we're facing. And you wonder what it will take for action to be affected. Thank you for that question.
CJ has a question. Go ahead, CJ.
Unmute myself. Yeah, my question is as inhospitable as it's going to be in Texas, if all of this comes to pass, I mean, do you see the expectation for population growth maybe being too optimistic and that more people will leave the state?
Yeah, I think so. I tried to get in touch with demographers to say, to what extent are you taking climate change into account? At some point, right, it has to become less desirable place. Unless, so I don't think so. I could be talking out of school here because I don't know for sure, but I've not seen that those demographic projections take the kinds of heat loads we're talking about into account. Yeah. So on the other hand, are we going to become more adapted to being inside more? I know my kids are, they'd rather sit and play the video games than to go outside and play the real games. Like, so here's me about to tell a story back in the good old days. We played in the dirt all day and we skinned our knees, and we have higher immune systems for it. That's a bit obnoxious, right? But what I'm saying is, are we going to become more comfortable with spending longer amounts of time indoors? Hey, it's nice and cool. We can control the climate. I get 800 channels streaming. I could see whatever I want. I don't have to go out into the environment. I think if we do, I think we lose. And we lose a lot in terms of our quality of life. There's an interesting field of study called ecotherapy that actually does peer-reviewed science quantifying the benefits of being outdoors. And I think if we lose that, I think we lose a lot. So answer your question, CJ, don't know. I could see it going either way.
Thank you.
Let's just take one or two more questions and before we let Jay go and probably have dinner. Gary? Gary, go ahead and unmute and ask your question.
This is just like when we taught together in class. Gary would always nap in the back when I was teaching.
Unmuting helps too. So Jay, can we learn anything from countries that are already in hot, arid climates with growing population, say wealthy countries in the Middle East, UAE or something? Are they doing anything that we can learn from?
Yeah, great question. Yeah, if they have the resources, it takes money to turn ocean water into drinking water.
Yep.
Desal, right? We're doing it in this country to a small extent. They're doing it to a larger extent. It's still, the technology, as I understand it, is still quite costly. I think other countries in the Middle East we could take a lesson from. We could look at Israel.
What's that?
Yeah, sorry.
Oh, yeah.
Was there a question? I was going to say we could look at Israel. They reuse, I think it's on the order of 70% of their gray water. So let me talk just for a second about gray water, right? You wash your hands, goes down the sink. It's a little bit of dirt from your hands in the soap. That's gray water, right? It's not like, it's not brown water or black water, which we don't have to talk about now, but that's gray water. And we reuse in this country very, very, very little of it. Less than it in Texas, probably less than 1% of all gray water is reused. And I've looked into it, right? And I thought about maybe taking the water that goes down the sink after I wash my hands and put it in my toilet tank and flush that. But do you realize when we go to the bathroom, we're peeing into drinking water, quality water? It takes a lot of time, effort, money, filtration to purify it. It takes a lot of energy to pump that high quality drinking water all over town. It takes a lot of energy to filter that water, to make it drinkable. And then we wind up just peeing in it and flushing in it. So instead of that, what if we just peed into the gray water that we use to wash our hands, fill up our toilet tank with that? And so, yeah, you have to hire a contractor and it's going to cost you a little bit of money. You need some PVC pipe and some check valves, but it's totally doable. And I understand it. It's like, I can't DIY that myself. I don't have the time, inclination, or handiness to do it. But if we're going to have 20 million new Texans moving here into all these new subdivisions, wouldn't it be very simple to pass an ordinance to say anyone who wants a permit to develop a new subdivision has to show how they're going to reuse 70% of their gray water in this way? And then it's not a contractor refitting something. It's just if it's in the planning stage, it's simply a line on a blueprint. And the amount of materials is pennies. It's just lost in the noise of how much it costs to build a home. So I think we're missing huge opportunities like that. It's simple technology advancements to help us be more conservative.
Well, thank you, Jay, for an informative and sobering presentation and some ideas for hope.
You're quite welcome. I appreciate all the great questions, and I'm looking at some of them in the chat. Really good questions. I appreciate the feedback.
Thank you so much. And thank you to everybody for being here and for participating.